I hope you have attempted the problem that I put before you to draw the complete or composite signal flow graph for our two basic equations for the speed control drive, the armature equation and the torque equation. Those are the only two equations we have. The problem was to draw the signal flow graph which will represent both these equations. And I told you that there was one condition that should be kept in mind, namely each node represents one and only one equation, because at each node you have some incoming arrows, and the equation says that the node signal is equal to the sum of the incoming signals multiplied by the transmittances of the edges that come to that node. Now, in our equations we had four basic variables: the applied voltage EA, the load torque TL, the armature current IA, and most importantly the motor speed omega m. So, omega m is common to two equations. It occurs in the electrical equation because the back EMF depends on the speed. It occurs in the mechanical equation because the frictional torque depends on the speed. So, omega m occurs in both the equations. Similarly, IA, the armature current, occurs in both the equations. In the electrical equation, it occurs in the form of armature drop IARA. In the mechanical equation, it occurs in the form of the motor torque KT into IA. The other two variables occur in only one equation, EA in the electrical equation, load torque in the mechanical equation. So, what are the different signal flow graphs that we could draw to represent these two equations? I am pointing out that for a given set of equations or even for a given block diagram, one may draw different signal flow graphs, because what one will choose is a different thing, and that depends on what the goal is and also on some experience with these things. So, what are the alternatives with the condition that I mentioned? So, I can have a signal flow graph in which there is a summation corresponding to the node EA, and that is of course very simple. EA equal to KB into omega m plus RA into IA. So, it is quite easy to represent that by an equation. The other equation is the torque equation, from which I can get TL, the load torque, equal to KTIA minus KF omega m, and so that is also very easy to represent. So, there will be a node TL and there will be two incoming arrows from the two variables or signals omega m and IA. So, this will be one signal flow graph which will be quite easy to draw, and probably you have already drawn it. So, there will be two input signals, because from these two nodes there will be only outgoing arrows, there will be no incoming arrows. So, from omega m and IA one can show arrows going towards a node called EA. So, omega m is multiplied by KB, the back EMF, IA is multiplied by RA, the armature resistance, and therefore the nodes signal EA equals KB omega m plus IARA. That is straightforward. The second one requires you to transpose the term TL on one side and the other two terms on the other side, but that is also pretty easy. So, TL equals the generated torque, which is KT into IA, minus the frictional torque, so minus KF into omega m. So, here is the complete signal flow graph which represents the two equations in which we have armature voltage EA and the load torque TL as two nodes which are not input nodes because they have incoming arrows, whereas omega m and IA are the two nodes which are input nodes because they have only outgoing arrows. Now what I am saying is that this signal flow graph is quite correct as it is. One of the signal flow graphs represents the equation for the armature, the other signal flow graph, the other part of it rather, represents the equation for the torque. Of course, if you compare this with the block diagram, in fact we drew two separate, we drew just one single block showing the motor and the load. We did not really show several separate blocks, but what we will do is we will do it as soon as we also look at some other alternatives for the signal flow graph. So what are the other choices and why we might prefer those choices? Well, as we saw earlier, the load torque TL, although it is really physically the output, the disturbance comes from changes in it. So we would like to regard TL as input. Similarly, the armature voltage EA, although hopefully it will remain constant, but there being no assurance that the supply voltage will remain constant, there will be a disturbance coming from EA also, and therefore EA also is profitably regarded as an input signal, although physically it is also an input signal. It is the thing that causes the motor to turn, etc. The other two signals which appear as input signals in this signal flow graph are, from a practical point of view, at least one of them, definitely of the nature of output, omega m. We want the motor not only to provide torque, but to provide torque at a particular speed. Remember, the function was to have the motor run at some desired speed, constant speed. So omega m is a natural output variable. What about the armature current IA, which is an input signal in this diagram? Well, it is not really an output in the sense one is not directly interested in the armature current per se, but it is not an input either in the sense you are not putting into the armature some current, rather we think of applying to the armature some voltage. So although this signal flow graph is correct, it is not a good one in the sense that it does not enable one to think of inputs and outputs the way we would like to. EA and TL as inputs, perhaps changes in them as disturbance inputs, and omega L and perhaps IA as outputs, or rather change in omega m as the output. That is, the thinking is changes in applied voltage, changes in the load torque, and these are physical signals, these are functions of time. Over a period of time they may change by small amount or by large amount. Changes in these will cause or will result in changes in the speed, and perhaps also or certainly also change in the armature current. Remember the distinction between variables, variable quantities, physical variable quantities, variables, or what we have called signals. All these four are signals or variables, and parameters, parameters of the system, such as the coefficients that appear as transmittances in the signal flow graph, the armature resistance, the torque and the back EMF constant, and the coefficient of friction, for example. These are not signals, they are not sort of functions of time in the same sense as omega is or EA is, although over long periods of time they may change. The armature resistance, because of heating of the motor armature, may start increasing. The back EMF and the torque constants may change because of change in the field current, but certainly we do not expect those changes to take place as rapidly and in an as unknown manner or surprising manner as perhaps changes in load torque and applied voltage. So on this signal flow graph, the signals, four signals appear, and also the four parameters of the system. This is, you can say, an advantage of the signal flow graph. It shows all the things fairly explicitly, whereas earlier we just drew a simple block and I put there the words motor and load, and I showed two arrows going in and two arrows coming out, and at that time of course I showed EA and TL as the inputs and omega m and IA as the outputs. So if I just draw a block like that, it only tells me that I am going to look upon these two quantities or variables as my outputs and these two quantities as my inputs. So I am going to think of in this way, that these inputs may change, they will in turn cause change in the output, how much, etc., etc. The block diagram itself does not give you any further information. You have to put it down in the form of equations, or as we saw earlier, sometimes you can put that information inside the block. Instead of just writing motor and load, I can put down what did we call it? We can put down the transfer function or various transfer functions associated with the equations, and we had seen that earlier. Now what would be another way of drawing the block diagram? So another choice would be just the opposite. We would have omega m and IA as the output variables, and therefore in this case we will write down equations, or from the equations we will solve for omega m and IA as sum of some two terms, and therefore then represent them on the signal flow graph. So in this case then EA and TL will be the input nodes, there will be no arrows going towards these two nodes. Omega m and IA will be the output nodes. How shall we relate the two? Unfortunately, omega m and IA appear in both the equations. So we will have to make a choice. I can either use the EMF equation to get an expression for omega m as a sum of two terms. That is not very difficult. It will be as follows: omega m is multiplied by KB. So think of transferring that to one side. So KB omega m equal to EA minus IARA. Therefore omega m will be 1 divided by KB into EA. So there is a transmittance from EA of 1 by KB. So I have put an arrow, a line with an arrow, and the transmittance is shown there. And the second term is the minus RAIA divided by KB. So here is the other line going from IA to omega m, and that is minus RAIA divided by KB. Therefore RA by KB minus RA by KB is the transmittance. So this represents the EMF equation, and we have solved the EMF equation, or rather we have rewritten the signal flow graph drawn so far represents that equation in a different form. Omega m is a sum of two terms. There are two signals coming towards omega m. So omega m is 1 by KB into EA minus RA by KB into IA. Just check that this is correct. Now we look at the second equation. However, now since I have already written down an equation in which omega m is the sum, therefore from the second equation now I cannot solve for omega m and express that as another sum. There is nothing wrong with writing that equation, but the way one draws and interprets the signal flow graph, this cannot be done. This is the one important condition that one must adhere to. So we can solve it for IA, because in fact it is very easy to solve for IA. Just divide through by KT. So then what do we get? We get IA equal to TL divided by KT. So here is one more edge going from TL to IA with a transmittance of 1 by KT, and we have another contribution which is KF into omega m divided by KT. So here will be an arrow that goes from omega m to IA with a transmittance of KF divided by KT. So this is another signal flow graph which is equally correct for the two equations, in which now EA and TL are the input nodes, omega m and IA are not input nodes because they have incoming arrows. Of course, you will notice that there is a difference between the two signal flow graphs that we have so far. Here is the signal flow graph with omega m and Ia as the inputs, Ea and TL as output nodes. I do not have to call them intermediate nodes because there are no outgoing arrows from them at all. And I have the second signal flow graph in which Ea and TL are the input nodes, omega m and Ia are the output nodes, and I can call them intermediate nodes also if I want, because omega m has an incoming arrow or two incoming arrows and an outgoing arrow. The armature current node also has two incoming arrows and one outgoing arrow. So there are these two signal flow graphs. Are there any further choices? Of course, we can combine one equation solved for one variable with another equation solved for another variable, only subject to the restriction that both of them should not express the same variable in terms of the others. So I should not solve each one for omega m or each one for Ia. There is no way of writing down those two equations or representing them on the signal flow graph. So you can think of the various choices that are there. From the electrical equation, I can either solve for Ea or omega m or Ia. From the mechanical equation, I can either solve for Ia or TL or omega m, but I can't solve both of them for omega m or both of them for Ia. So one could draw some more signal flow graphs. For example, there could be a following signal flow graph which will be a little different. The torque equation is solved for omega m. Instead of solving the EMF equation or the armature equation, circuit equation for omega m, suppose we look at the torque equation and solve it for omega m. So what will then be the result? Omega m will be a combination of, in the torque equation we have load torque and armature current, and anticipating that I am going to solve the other equation for the armature current Ia. So from TL to omega m, what will be the transmittance? TL plus Kf omega m. So TL goes to the other side and divide by Kf. So the transmittance is minus 1 by Kf. And what is the transmittance from the armature current to omega m? KTIA equal to TL plus Kf omega m. So the transmittance will be KT divided by Kf. So this part of the total signal flow graph which we are going to draw will represent the torque equation expressing omega m as a sum of two signals. Now if you go back to the first equation, I should not solve it for omega m, and since we would prefer to see Ia as an output, I will solve it for Ia instead. What will happen then? IARA equal to Ea minus Kb into omega m. So there will be an arrow going from Ea to Ia, and what will be the transmittance? The transmittance will be 1 by Ra, because IARA equal to Ea minus Kb omega m, and there will be an arrow from omega m to Ia, and what will be the transmittance of that? It will be minus Kb divided by Ra. So here is a different signal flow graph, and you can compare it with the graph that we drew earlier. Same input nodes Ea and TL, Ea and TL here also, same output nodes omega m and Ia, omega m and Ia here also. So the same choice of input nodes, same choice of output nodes, but the two graphs look different, and that's quite okay. There's nothing wrong about it. There's no need to get worried. Although the textbook may draw it in one particular way, or your teacher may be in the habit of drawing it in one particular way, nobody can say that either of these or both of them are wrong. Both of them are correct, and in fact there may be a few more signal flow graphs that you could draw. Do try to draw those other signal flow graphs to get practice. But to proceed further, either of these two signal graphs would be good enough. In fact, the first one that we drew also will be a correct graph, and we will see whether it is good or bad, or what is the difference between these various signal flow graphs and why we may prefer one over the other. Okay. So, now that we have drawn the signal flow graphs, we have put down in a graphical form all the information that we know about the system, namely the relationships between the various signals. So, now we can leave behind those equations and concentrate on the graph. Now, Mason, as I told you, gave a rule, or one can write it in the form of a formula, and it is called Mason's gain formula, because we will see that some terms that appear in the formula look like gains. These are the multipliers in any one of these blocks, transmittances. So, we can now take a look at the statement of Mason's gain formula and apply it to each one of our two equally correct signal flow graphs, where omega m and Ia appear as output nodes and armature voltage and load torque appear as input nodes. And we will also take a look at the earlier, the very first signal flow graph, which was very simple, in which the things were just the other way around, and see what is the difference. Now, Mason's gain formula, or his rule, in the beginning may sound fairly complicated, and it is complicated because it is meant for not a very simple signal flow graph like the ones that we have looked at, in which the number of nodes is very small and two of them are input nodes only, so there are no incoming arrows. It is a rule which will apply to a signal flow graph which may have a larger number of nodes with all kinds of transmittances, with no restriction on transmittances. In fact, Mason allowed something which is very peculiar, which is called a self loop, because it looks like a loop, all right. At the moment we do not have that in our signal flow graph, but when Mason introduced this idea in his very first paper, what he did was he suggested, or he gave some simple rules for manipulation of the signal flow graph, that is transformation of the signal flow graph. You have a signal flow graph that looks fairly complicated, and so you can't make out what is the relationship between the variables other than the equations at the nodes. For example, what we did earlier, I do not see it here, that omega m in terms of load torque and armature voltage, or armature current in terms of load torque and armature voltage, because I have the two equations, but in each of the equations the other quantity appears. In the armature equation both omega m and Ia appear, in the torque equation both omega m and Ia appear, whereas I want an expression for omega m only in terms of Ea and TL, that is with Ia eliminated. Similarly, one may need an expression for the armature current in terms of the armature voltage and the load torque with the speed eliminated from the equations. And in fact, this is how you normally solve algebraic equations, do not you? If you have what are called simultaneous linear algebraic equations, maybe 3 equations in 3 variables or larger number, you use this method of elimination of variables and essentially end up finally getting one equation in only one unknown, and do this in different ways so that you get expressions for all the unknowns. And one of the rules associated there is of this sort. What is it called? Who is it named after? You may remember a rule called Cramer's rule, in connection with determinants or simultaneous linear equations. It is not surprising that Mason's gain formula is a sort of a way of using Cramer's rule for solving a system of simultaneous linear equations. The only thing is, Cramer's rule requires you to write down the equations in a particular way, for example, in the form of a matrix and a vector and so on, nicely arranged set of equations, and then you look at some determinants and so on. In Mason's rule, you do not have equations written in that form at all. In fact, you do not write equations, you write them symbolically or graphically in the form of the signal flow graph, and there are no determinants to be calculated, there are some quantities to be calculated or obtained from the graph. So, it is a sort of a graphical or a pictorial version of Cramer's rule. So, the first thing that Mason was doing was to give you rules of transformation of signal flow graphs, and at one time that used to be an interesting topic. In fact, it is still a good topic for getting some practice, what is called signal flow graph manipulation or transformation, or you can do the same thing with block diagrams, then it is called block diagram manipulation or block diagram transformation. And when I studied my subject many years ago, I spent some time looking at these things, block diagram transformations and signal flow graph transformations. But today, of course, there are so many other things that we have to learn, so we do not have time for everything. Also, as I told you, signal flow graph is really to be used by a human being for a small problem. For a big problem, we have to do things differently, and today, of course, we make use of computer program or computer packages. But just to illustrate this idea of signal flow graph transformation or manipulation, there is one simple system that I can look at, not system really, a simple signal flow graph. It is so simple that you do not really have to draw a graph, a signal flow graph for the equations that are involved. But suppose we have three signals x, y, z, and there are two relationships which are put down on the signal flow graph like this. So, what are the relationships? Y equal to k1x and z equal to k2y. There is only one input node x and there are two other nodes y and z. Each one of them has incoming arrows, so it corresponds to an equation. Of course, y has an incoming as well as an outgoing arrow. Now, suppose you have this simple signal flow graph, then what can you do with it? One can see immediately that the variable y can be eliminated, that is, the signal y can be made to disappear from the signal flow graph to draw a new signal flow graph, because you may not be interested in this y. In fact, truly this y may be what I have called earlier an intermediate variable. It is not a variable directly of interest to us, it is neither input nor output. Now, it is easy to eliminate it, because even a high school student can do that. Y equal to k1x, z equal to k2y. So, substituting for y in z equal to k2y, we will get z equal to k1 k2 into x. So, here is a simple transformation rule for signal flow graphs. That is, if you have a configuration like this, that is, there is an intermediate node y to which there is an incoming arrow exactly 1. So, there is a very simple equation y equal to k1x, and there is an outgoing arrow, in this case exactly 1, then that intermediate node can be eliminated. Of course, this is a very simple rule indeed, and if Mason stopped with this, then one would not appreciate his work. But you can think of a more complex situation where you have a signal flow graph which is a little more complex. So, I have x input node, then there is an intermediate node y which is connected with x through a transmittance k1, but y feeds into two different signals. Let us say some signal W with a transmittance K2 and some signal Z with a transmittance K3. Okay, this is different from the earlier one. Earlier one we had almost straight transmission, X going through Z through Y. In fact, that kind of a connection is given a name. If you thought of that K1 and K2 as some physical blocks or systems, that kind of connection is given a name. What is it called? It is called tandem connection, one after another. It should not be called a series connection, because series can be confused with series connection of electrical components. We are not talking about series connection of components, we are talking about connection of blocks or systems. So tandem connection, or sometimes it is also called the chain connection. Like a chain, you have a chain of these blocks or systems, one coming after another. And so that rule, that simple transformation rule, applied to a tandem or a chain connection of transmittances. But this situation is a little more complex. We have an intermediate node, however, Y. Now can we get rid of it? Yes, and as you can see, it will be just one more step beyond the earlier rule, because now I have W equal to K2Y and Y equal to K1X. So W equal to K2 into K1X. So I can directly draw an arrow between X and W with a transmittance K1, K2. But I should not forget about the other node Z. The other node Z is also a signal which may be important or useful later on. So I can't leave that node alone. In fact, if you leave a node alone, which means you have no equation for it, you can have a convention that the equation says Z equal to 0. There is nothing coming into it, so the signal is equal to 0. Now, but we have Z equal to K3Y and Y equal to K1X. Therefore, I must put another transmittance from X to Z of value K1, K3. So I can eliminate the intermediate node Y, but now I have to replace two new edges or transmittances. Now what is the point of doing these transformations? Because why are these transformations to be done or thought of at all? Because they simplify the graph. Here, for example, the graph had 3 nodes. After transformation it has only 2 nodes. But there is a flip side to it, that in doing this we have removed the signal Y. It may happen that the signal Y is also useful or required later on, and therefore what one does is one then goes back after you have worked with X and Z without Y, then you go back to Y, and that's easy because Y is simply K1X. Similarly, in this case we had 4 nodes, we have eliminated one, so we have only 3 nodes now. So we can go on, maybe carry out some further transformation, simplification, elimination, and finally, of course, once we have some relationship, we can find out Y, we can always go back to Y as K1X. There is no problem whatsoever. So there are a number of such rules, transformation rules, that Mason looked at, and they are all there in his very first paper on this signal flow graph representation of system equations. Mason must have realized while doing these transformations that something interesting could come out of it, and that is what perhaps led him to give his gain formula or rule. And today we can see what is it that could have given rise to Mason's gain formula and made him to sort of persist and go ahead and try to get something interesting, not very obvious, from the signal flow graph. Let us go back to our very first simple minded signal flow graph with omega m and IA as the inputs, EA and TL as the outputs. As you can see from the signal flow graph, there is hardly any work to be done, in the sense EA is equal to omega m into some transmittance plus IA into some transmittance, TL is equal to omega m into some other transmittance plus IA into some further different transmittance. So I already have expressions for EA and TL in terms of omega m and IA. If that is what I wanted, then there is nothing more to be done. In fact, I may not have drawn the signal flow graph at all. Whereas the other two graphs that we have got, they are a little more complex, or they are different. I look at the node omega m, I get a relationship expressing omega m in terms of TL and IA. I look at the other node IA, I get IA in terms of omega m and EA. So omega m involves IA, IA involves omega m. And how does this appear on the graph? It appears in the graph in the form of a loop or a closed path. For example, here is a path. If I want to trace it, starting with omega m through the transmittance minus KB by RA, I will go to the node IA. From the node IA through the transmittance KT by KF, I come back to the node omega m. So omega m to IA back to omega m, that is referred to as a loop or a closed path. And of course, I must look upon it, the arrows, as one way streets. So I should go in the correct direction. So when I trace the closed loop or path, I should go from omega m to IA through minus KB RA divided by RA, and from IA back to omega m through this transmittance KT divided by KF. Of course, I could start going around the loop from IA. So from IA I go to KT by KF to omega m, and then from omega m I come back to IA through minus KB by RA. So whichever way I want to do it, I can trace the loop, but I must trace it in the correct direction. So there is nothing like starting node, because I come back to that node. So in a loop, every point can be a starting point where you again finish. So that way there is no difference between the two. But there is a loop, and this loop goes with the fact that for omega m I have an expression in which IA is involved, and for IA I have an expression in which omega m is involved. Whereas, as we saw, and we did this earlier, we want an expression for omega m in terms of EA and TL alone. We do not want armature current. If possible, we want an expression for the speed in terms of the armature voltage and the load torque only, which therefore means that if I wrote down the equations, I will have to eliminate IA as the unwanted variable. Now, if you look at the signal flow graph, I cannot eliminate either omega m or IA very simply, because it is not like the earlier case where we had a tandem connection and an intermediate node which could be eliminated easily, or a connection where from a node we branch off to two different nodes, so that intermediate node also could be removed very easily. That is not the case here. We have this loop situation. The other signal flow graph that we drew also has exactly the same feature. There is a loop occurring there. Of course, if you look at it carefully, you will see that the transmittances are different. In one case, IA to omega m it is KT by KF, in the other case omega m to IA it is KF by KT. Similarly, from omega m to IA it is minus KB by RA, from IA to omega m it is minus RA by KB. So the transmittances are just the reciprocals, they are not the same. Well, that has happened because we solve the equation for one or the other, depending on that one transmittance appears or it is reciprocal. But in either case we have a loop. Now what Mason noticed therefore is that this is a situation where you have to eliminate one of the nodes, and therefore he thought of a rule for elimination of the node. Of course, that requires redrawing the signal flow graph, just as we redrew the signal flow graph by removing the intermediate node Y. I will have to start with one of the signal flow graphs and do this some operation on the signal flow graph to remove one of the nodes. But eventually Mason probably saw that we can do it in such a way that we do not have to remove anything from the graph, But of course you have a rule which is a little more complicated, and as I said, no wonder it is complicated, because a signal flow graph could have a large number of signals or nodes, and they could be connected in various crisscross ways. In our two signal flow graphs, each one of them has only one loop. There are signal flow graphs which you can draw for actual control systems which will have more than one loop, and I mentioned feedback control systems. We had talked about this feedback loop, and I had said that in chemical process situation where there are a large number of variables which are to be controlled, there are a large number of feedback signals, and therefore there is more than one loop. So if you draw the signal flow graph for a chemical process example, not a very simple but maybe even a practical one, you will end up getting quite a number of loops. So the rule has to be complicated because it has to account for, or it has to take care of such complex situations. But once you understand what are the various terms or words that are used in the rule, what do they mean in terms of the signal flow graph, and take care with some of the signs that have to be looked at, the rule is not that difficult at all. And so I will get started with a description of the rule. Now what the rule says, or the rule enables you to write down, is the following. To start with, the rule tells you that you can obtain an expression for node signals which do not correspond to input nodes in terms of the input node signals. That is, you can write down expressions for each one of the non-input nodes in terms of the input node signals. So for example, omega m and Ia are the non-input node signals, Ea and Tl are the input node signals. So I can write expressions for each one of these non-input node signals in terms of the input node signals. And what do I mean by write in terms of? What I mean is, I can write down an expression like omega m equals some expression, and Mason's rule tells you what this expression will be or how to write it down, multiplying one of the two input node signals, in this case say Ea, plus another expression multiplying the other input node signal, in this case Tl. And that's exactly what we want. We want an expression for omega m in terms of Ea and Tl. These two expressions, or what eventually we may call coefficients, that multiply Ea and Tl, and therefore you could even think of them as some kind of transmittances from Ea and Tl to omega m. Mason's rule or gain formula enables you to write down these two. In fact, when I have filled in the expressions, I have a formula, and that's why it is called the gain formula, although strictly speaking it should be really called Mason's rule. Similarly, for the other non-input node Ia, I will be able to write down some expression into Ea plus some other expression into Tl, so that if I need to look at the armature current, I can also use this expression. Of course, if I am only interested in the speed and I am not worried about the armature current, because speed is the main thing of importance to us, then I need not write down the other equation. But the rule will enable you to write down the other equation as well. So that is how Mason's rule, or that is the final outcome of applying Mason's rule. You will be able to write down an expression for a non-input node signal equal to a sum of the various input node signals multiplied by some coefficients or transmittances, and the rule tells you how to write down the transmittances. You will see, if you remember your school algebra, that there is a similarity between this and Cramer's rule, because Cramer's rule also enables you to do the same thing. If x1, x2, xn are the n unknowns in the equation, linear equations, and on the right hand side of the equations as we usually write them are some quantities, say b1, b2, bn, then we have x1. In Cramer's rule, of course, x1 is a ratio of two things, but those two things can be written as b1 multiplied by some coefficient plus b2 multiplied by something plus, and the last term is bn multiplied by some coefficient. So it's very much like Cramer's rule, although not in the usual form. In the usual form, Cramer's rule is simply x1 equal to one determinant divided by another determinant, but if you expand the numerator determinant, then you will get a summation. So in fact, these bracketed expressions that the rule tells you how to write are in a way determinants of some kind, and the rule tells you really how to write down these determinants without going through the usual procedure of Laplace's expansion or whatever. Mason has done that work for you and has produced this rule. There are of course other earlier attempts which were made to handle simultaneous linear equations. Cramer's rule was satisfactory, all right, but it involved computation of determinants, and therefore naturally a rule which enabled you to compute the determinants in some shortcut way would be desirable. And I found out that one of the persons who was associated or who really introduced the concept of a matrix, the English mathematician Cayley, had something to say about this. In fact, he gave a way of evaluating determinants which amounts to writing a signal flow graph corresponding to the determinant and then doing some work on that signal flow graph as of the same kind that we are going to see. He was of course more interested in evaluating determinants rather than in solving systems of equations or any block diagram or signal flow graph manipulations. He was not looking at physical system equations as such. He was only looking at the problem of solving simultaneous linear equations. But Cayley gave a rule which looks very much like Mason's gain rule or formula. Okay, so now let us choose this particular signal flow graph. I will express omega m in terms of Ea as omega m equal to some coefficient multiplying Ea plus another coefficient multiplying TL. So suppose I look at only the first part of it, how does omega m depend on Ea? That is, in that expression omega m equal to what multiplied by Ea plus the other term that involves TL. What is the coefficient that multiplies Ea? Now to obtain that coefficient from the signal flow graph, one introduces the almost obvious idea of a path from the input node, in this case Ea, to the node whose signal you are evaluating or you are trying to find an expression for. So we look at a path from Ea to omega m. This almost looks like our forward path in the control system block diagram. In fact, when we get back to the control system problem with feedback, we will see that it is almost close to that. But at the moment we need not worry about forward and backward, because from an input node you can go only in one direction. So it is only a forward path anyway. So for this, first we need to find out paths from the particular input node that you are looking at to the particular non-input node that also you are looking at, namely in this case path from Ea to omega m. What are the paths from Ea to omega m? Of course, there is this path Ea to omega m through that 1 by kb. Is there any other path? Now this is where you have to be careful. For example, if I were to sort of think of this as some road network and I wanted to move around the city, of course the roads are all one-way roads, there are arrows, and I wanted to go from Ea to omega m, how would I go? Well, I can go of course directly along this transmittance 1 by kb along that road, I will reach omega m. But let us say I was absent minded, or I just wanted to roam around a little bit. So then instead of stopping there, I go on to IA and then come back to omega m. So EA to omega m to IA back to omega m. Does that count as a path or not? In practical terms it may. Of course, if I do it this way, a policeman who might be watching might get suspicious as to why this person is going from omega m junction to IA and then back to omega m. Has he lost his way or something, or is he up to some mischief? In this case, we do not allow such a thing. The rule says that by path we mean something where the same node will not be visited again. So EA to omega m is okay, but EA to omega m to IA to omega m is not to be chosen. That is the way the rule is, because that is the way the determinant expansion will have it. So we are not to do it that way. So then what are all the paths from EA to omega m? There is only one, namely this edge 1 by kb. And so with that forward path then, or with that path from EA to omega m, we have a single transmittance 1 by kb. So that is one thing that we have to first of all work out. Find out all the paths from an input node that we are looking at to the other node that we are looking at. In this case, I want to have an expression or a part of an expression for omega m in terms of EA. So I am concentrating on EA as the input node and omega m as the node for which I want to write down an expression. In this case, there is only one path. But of course, in a very complex signal flow graph with a large number of nodes, with large number of transmittances connected in various ways, there could be more than one forward path. And just to make sure that we are all together, I will take an example, just a numerical example, not representing any physical system, where there is more than one path between a node which is an input node. Incidentally, some books might use the word source node. In fact, Mason used that term. And a node which is an output node is called a sink node. For control theory people, input and output is a more appropriate choice of terms than source and sink. So path, or all the paths, have to be found out. The second thing that we have to find out is all the loops or closed paths in the signal flow graph. In the signal flow graph that we are looking at, either of them, the loop sort of stands out immediately. And this is where the advantage of the signal flow graph technique is, that as a human being, if I look at a graph like this and the graph is not too complex, I can immediately spot the closed loop or the closed path. So there is this closed path which involves omega m and IA, omega m to IA through some transmittance and then back to omega m through another transmittance. So this is a loop. With that loop is associated what Mason called the loop gain. That is the product of the transmittances along that loop. So in this case, kf by kt multiplied by minus Ra by kb. This is the loop gain. There is only one loop here, and the loop gain therefore is kf by kt. This is one of the transmittances multiplied by the other transmittance. Don't worry about the negative sign, minus Ra divided by kb. So this is the loop gain associated with that loop. In general, you have to identify all the loops, and there may be more than one loop. So for each one of the loops, you have to find out, or you have to calculate the loop gain. Now when the signal flow graph is complex, there is more than one loop, one should not be overconfident and say that I have found out all the loops that there are in the graph. one has to make sure that you are not missed out any loops, and so it's good to do it in some systematic way. For example, I can ask, is there any loop that involves the node EA? No, the answer is no, because EA is an input node, an arrow only goes out of EA, an arrow never comes back to EA. So EA cannot be in any loop, but omega m could be, because there is an incoming arrow and there is an outgoing arrow. Similarly, IA could be in a loop, but not TL. So this can be done systematically, that given a signal flow graph, first of all, input nodes are excluded from loops, they don't lie in any loops because there are only outgoing arrows, and the other nodes you can check whether there are any nodes which have both incoming and outgoing arrows. There may be some nodes which have only incoming arrows, and as I told you earlier, they can be introduced, fictitious nodes can be introduced to ensure that that happens. Otherwise, many of these nodes will have both incoming and outgoing arrows, and then one tries to trace the closed paths or loops carefully one by one. In our figure, there is only one loop, so there is only one loop gain to be calculated, and that is what I have calculated. Now, the next part is a little harder, and we will take up an example to illustrate that, but let me first state it and then we will look at the example where there will be more than one loop. When there is only one loop, as in this case, then just write down the expression 1 minus that loop gain, 1 minus the loop gain. So in this case it will be 1 minus Kf by Kt into minus Ra by Kb. Therefore that minus minus will cancel if you are worried by that minus sign, and you will get 1 plus Kf Ra divided by Kt into Kb, and if I assume Kt equal to Kb, which is usually the case, then I will get Kb square in place of Kt into Kb. So if there is only one loop, then the rule is as simple as that, simply 1 minus loop gain, that is the next thing to be calculated. But if there is more than one loop present in the signal flow graph, then some more work is to be done. What is the work to be done? First thing, you select the loops in pairs, select a loop pair, a pair of loops. There may be one loop here, there may be another loop here, but select them in such a way that the two loops have no nodes in common at all, and such a situation is referred to as non-touching loops. So I look at a pair of loops and make sure that they are non-touching, they do not have any node in common, they will not have an edge in common certainly, but they should not even have any node in common. So we need non-touching loops. So a pair of non-touching loops. What do I do with them then? For such a pair, I take the product of the loop gains, and I take all such non-touching loop pairs, take their loop gain products 2 by 2 and add them up. So I have 1 minus, if you have more than one loop, then it is not just 1 minus loop gain as I said earlier for our problem, but it will be 1 minus the sum of all the loop gains, all loop gains, whether they touch each other or not, all the loop gains, plus the sum of loop gain pair products but non-touching. So sum of product of two non-touching loop or their gains, all possible loop pairs which are non-touching, take the loop gain products and add them up, that is the next term. So the sum of all products of two loop gains subject to this non-touching condition. But that is not all. If there are more than two loops, I will have to look at a possibility that there are 3 loops which are non-touching pairwise, each one of them does not touch the other 2. Then I have to take the negative of the sum of product of such 3 loop gains, and then plus again the sum of product of 4 non-touching loop gains, and go on till I have exhausted as large a collection of loop gains as I can find. Maybe I end up having 6 loops finally which are non-touching to each other, but the moment I look at 7, I find that some 2 of them are going to touch each other, so I stop there with the non-touching loops, as many as possible. So I have to calculate this expression. This expression will be the denominator in my multiplier for that input signal. So for our problem, fortunately, the calculation is very simple. I simply have 1 minus loop gain, and therefore I have 1 plus kf Ra divided by kt into kb. That is going to be the denominator of the multiplier for Ea, and this denominator, because it is really related to a determinant, is sometimes called delta for the signal flow graph. In fact, this same delta will appear in all the terms. In this case, this delta was simply 1 minus loop gain, but it could be 1 minus loop gain or sum of all loop gains plus sum of 2 non-touching loop gains minus sum of products of 3 non-touching loop gains, etc., going on till as many as you can get non-touching loops. That is the denominator part, and the numerator part is obtained a little easily. You have found out a forward path or a path from the input node to the node under consideration. Look at the denominator expression and get rid of all those terms which involve a loop which touches this forward path. For example, our forward path from Ea to omega m touches this loop which involves omega m and Ia. So I remove that term. So what remains from that? Only 1. So the numerator in this case will be only 1, and this 1 is to be multiplied by the transmittance of that path. So this 1 is to be multiplied by 1 by kb, and therefore my expression for omega m in this case, as far as the term containing Ea is concerned, will be omega m equal to 1 by kb divided by 1 plus kf Ra divided by kt kb, this whole expression multiplying Ea. But there is the other term that depends on the load torque, so plus something else multiplying the load torque. Now if you have followed what I have said so far, you should be able to write down that second multiplier in the same way as we wrote the first multiplier. The denominator, which is 1 minus sum of loop gains plus sum of products of 2 loop gains, etc., etc. The numerator is the transmittance of that forward path multiplied by the denominator expression, only choosing those terms that do not touch the forward path. That is, only keeping those loop gains which do not touch the forward path. But do not forget about that 1, that term 1 remains in the numerator also. So do not remove that term 1. Only the loop gains which touch the forward path are to be removed, and the rest of the loop gains are to be retained. So in other words, you are looking at loops which do not touch the forward path and also do not touch each other. So this is the way to write down the expression or the multiplier for each one of the input signals. So apply this for our signal flow graph to complete this problem and get the expression for omega m in terms of Ea and TL, and then compare it with the expression that we had obtained earlier. It's arranged differently, but it must be the same formula finally. And then you can repeat this with the other signal flow graph that we drew for the same system, choosing a somewhat different arrangement, but both omega m and Ia as the output nodes. Apply it to that signal flow graph and check that you will get the same expression. So whichever way you draw the signal flow graph, the final answer will be the same, and that's the way it should be, because we don't expect that from that we will get 2 or more differing answers.